Hello everyone, we will continue with our lecture series, and previously we have studied various state space representations both for linear and nonlinear systems. But if we want to design a linear control system or even want to analyze the stability or controllability, things like that for linear systems, first thing to do is the linearization of nonlinear systems, because most of the real systems are nonlinear anyway. But the tools and techniques that we have are valid for linear systems. So, we have to have some way of linearizing a nonlinear system. So, that is the topic of this lecture actually. So, we will see how to start with a nonlinear system and what do you mean by linearized system actually. And okay, before when I proceed, the point here is many I mean, even if we tell that the systems are linear systems, I mean most likely it is actually a linearized system. So, that means in reality there is no linear system per se, in very rare case you may have it actually, but by implicitly we mean linear systems means linearized about some operating point and things like that actually. So, that is why we will study in detail how to get these linear systems actually. So, what is the problem? Problem statement is something like this. Given a nonlinear system like this, x dot equal to f of x u, okay, we want to derive an approximate linear system. Remember, this is an approximate linear system. That means, the system that we are talking about never replaces this system, but this is only an approximation about an operating point x 0 u 0. Okay. So, this particular thing what you see here x dot equal to x plus b u can have different values of a and b as as you keep on changing this operating point x 0 u 0. Okay. So, this nonlinear system can remain same, but the linearized system can be, we will also give an example. Linearized system can be different when you change the operating point actually. Okay. Now, also remember the by operating point we do not necessarily mean that it is a equilibrium point. Okay. Equilibrium point just happens to be one of the operating points actually. So, what is operating point now? By definition, an operating point is a point through which the system trajectory passes. Okay. That means, if the system trajectory starts with some initial condition somewhere and then it follows a certain trajectory, associated with that there is a control like a noise bell, and you take any pair anywhere actually and you consider that as x 0 u 0, then about which the system dynamics A and B matrices can be found out, and that is what is called an operating point. Now, equilibrium points are special class of operating points, because if the system is stable, ultimately the system goes to the equilibrium point, and by definition equilibrium point will satisfy the differential equation anyway. If we substitute any equilibrium point, then this will become 0 and this equation will also become 0 actually. That is the definition of equilibrium point anyway. So, equilibrium point happens to be just an operating point, but in general we linearize the system dynamics about operating points actually. Okay, and by definition operating point is a point through which the system trajectory passes. Okay. That means, you can also talk about a nominal trajectory altogether. Okay. That means, x of t u of t, that is a nominal trajectory about which you can keep on getting a time varying linear system. A of t and b of t will result from there, and then you can talk about a time varying linearized system with respect to a nominal trajectory, not a nominal point really. Okay. So, that is also possible actually. So, let us see how to do that. Before we proceed, we will start with a very simple idea. Okay. Let us say there is a scalar system x dot equal to f of x, x is just a scalar. Okay. There is an operating point somewhere. Okay. The way to find the operating point is we will not talk too much on that. If you do not have anything, then probably naturally the points to select is equilibrium point, and by the equilibrium point what you need to do is just put this equal to 0, okay, x dot, because that is the definition of equilibrium point, and then associated with that we do some assumptions about, okay, this will result in, let us say, n dimension, n equations actually. Okay. But x is n dimensional and u is m dimensional, remember that. So, we need to have m further assumptions for that. Okay. So, that the number of equations and number of variables will be equal, from which you can solve this system actually. right. This system consists of n plus m variables, and this equation is only n equations. So, we need to have m approximations, okay, so that this number of equations and number of variables are same. So, we can solve it from there actually. Okay. So, these assumptions can be either in control variable or in state variable. For example, if you want this straight and level flight in flight dynamics, we consider altitude being being known to us, that means altitude is a state variable. Okay. You can also talk about, okay, it is a straight and level flight. So, I do not have lateral dynamics. So, delta and delta r, that means aileron and rudder surface deflections are 0. That means, these two equations along with h equal to some value, okay, those becomes kind of input to this equation, that means, those are known to this, and then you can put this system equal to 0 and solve it. Okay. I hope this is clear. So, now let us continue with that. So, what you are telling here is just a scalar system, okay. We have an operating point. Okay. So, we want to find a linearized system about that actually. Okay. So, what are you doing? What you are trying to do is perturbation analysis really. So, any point of time, let us say, okay, we consider this x as a perturbation about x 0. Remember, x 0 is an operating point. Okay. So, that means x is equal to x 0 plus delta x. Okay. That is what we are interpreting actually, and this is not approximately equal to, this is equal to. Okay. This is x equal to x 0 plus delta x, that is our definition actually. So, we want to find out a dynamics for delta x using this original dynamics, that is what our aim actually. Okay. So, how do you do that? So, obviously, if you substitute x 0 plus delta x, there is a term called x 0 plus delta x here, f of x 0 plus delta x. So, obviously, when we see this term something like this x 0 plus delta x, we intend to expand it using Taylor series actually. Okay. So, what are you doing here? You are substituting this expression back in there. So, the left hand side is nothing but x 0 dot plus delta x dot, that is what it is, okay. And then that is equal to f of x 0 plus delta x, and this f of x 0 plus delta x we are expanding using Taylor series. So, what are you getting? If I use it using Taylor series, you expand it about x 0, then the first term is f of x 0, second term is del f by del x, that means, in this case it will be df by dx. So, f dash of x evaluated at x 0 times delta x, then this the second derivative evaluated at x 0 times delta x whole square divided by 2 factorial, like that it will continue. That is a standard Taylor series anyway. Now, what we are doing here is we are assuming that delta x is small, that is why this perturbation theory and all that is valid, because the inherent assumption is delta x is small, and if delta x is small, delta x square and then cube and other things are small, and those are also divided by 2 factorial 3 factorial like that actually. So, the entire term becomes a small quantity under that assumption that delta x is small. So, that means, these are higher order terms, or what we typically call as hot terms, okay, that means higher order terms. Okay. Normally, we do not want to touch that actually. So, that means, we neglect these higher order terms actually. Okay. So, what are you left out is something like now this equal to, when you leave out this one, when you neglect this equal to is no more valid. So, you have an approximately equal to term now. So, that means, neglecting, if you once you neglect higher order terms, the left hand side what you get here is approximately equal to this only the first term plus the first order term. This is also called 0th order term, there is no delta x, that means delta x to the power 0 basically. So, you have up to first order term you keep, okay. So, then it becomes approximately equal to. Now, what is the observation? Observation is x 0 is an operating point, that means, if I substitute x 0 over here, it satisfies the differential equation. By definition, x 0 is a point through which system trajectory passes. That means, x 0 will certainly satisfy this equation exactly basically, right. That is the definition of system trajectory. Okay. Any point you select from the trajectory, this will satisfy the differential equation, otherwise the system trajectory does not pass through that actually. So, that means, this x 0 point exactly satisfies this equation. So, what is the implication? This first term and this first term will cancel out, okay. This is exactly equal to that. Okay. So, that is what you do here, and what are left out? You are left out with this term being approximately equal to that term. Okay. So, that is what you are doing here. So, the x 0 satisfies the differential equation exactly. So, that is why this is equal, this is valid, and this leads to this equation actually. Okay. Essentially, well, you can I mean theoretically speaking, this is no more equal to basically. So, what you can do, I mean what you are telling is approximately equal to really. Okay. So, delta x dot is approximately equal to that term, I mean f dash of x 0 times delta x. So, we define this term f dash of x 0 as some quantity. Remember this is actually a scalar problem. So, that means this is just a number actually. Okay. So, this number we define it as a, okay, and then we are okay. So, that means this is our convenience actually. So, we just define this quantity as a, okay, and then we are left out with a times delta x actually. Okay. Okay. And then we, so that means what, we are getting a linearized system as delta x dot equal to a times delta x. That is the linearized system actually, approximate system around or about x 0 operating point actually. But we do not want to keep on writing delta x dot everywhere actually. So, under the implicit assumption, we redefine the variable and we do not want to redefine to a different variable. Let us say we simply little abuse of notation we do with the assumption that I mean with the assumption that we know what we are doing here. That means x is redefined as delta x actually here. So, in that sense what you are getting x dot is a x actually, where a is nothing but f dash of x. But remember this x dot whatever x you are getting here, this x is nothing but this delta x, and this delta x is meaningful only when you know a x 0. So, this particular delta x what you see is meaningful only with the knowledge of x 0. Okay. So, that is sometimes we keep it silent, we implicitly assume that is origin, that is 0 0 0 and things like that. But always remember that delta x is not equal to x in general, and delta x is meaningful only when the knowledge of x 0 is available to us actually. Okay. So, but anyway the what we are getting here ultimately is x dot is equal to x, we keep on writing, we do not want to write approximately equal to all the time. So, we write okay, as far as the linearized system is concerned, x dot equal to x, where a is nothing but this term, well this term evaluated at x 0. Okay. So, that means this is actually x 0, okay, this one. Okay. So, f dash of x, that means this is actually f dash, you carry out the f dash of expression, then evaluate it about x 0, that is what the term actually, that is what it means. Okay. Alright. So, this is all about a scalar homogeneous system. So, we are not confined only with that. So, we will slowly build up towards more general systems and all. Before going there, let us go through a simple example actually. Okay. So, we have let us say a nonlinear system which is x dot is equal to x square minus 1, and also remember x, I mean these operating points are given to us as plus or minus 1, which is also happens to be equilibrium point. Okay. By default these are taken like that most of the time. So, why you are getting, how are you getting that? You are putting simply that this is equal to 0, that means x square equal to 1 and hence x equal to plus or minus 1, and if you substitute that it will also satisfy the differential equation obviously. Okay. So, it happens to be there are two equilibrium points for this problem, one happens to be plus 1, one happens to be minus 1. Okay. And we know we already have derived this equation. So, we do not have to keep on doing it again and again. So, we know that x dot equal to x is a linear system where a can be given like that. So, we directly evaluate a here. So, let us say in one case where we are taking x 0 equal to 1, that is a 1, and when you take x equal to minus 1, that is a 2. Okay. But both of the formulas are del f by del x evaluated at x 0 equal to 1 or del f by del x evaluated at x 0 equal to minus 1. Okay. What is del f by del x here? 2x actually. Okay. So, this is evaluated 2x evaluated at x 0 equal to 1 and this is 2x evaluated at x 0 equal to minus 1 actually. So, that means what you are getting here, this in this case it is 2 and this case it is minus 2. So, the linearized system is like, even though the nonlinear system is whatever you had in the beginning, for the same nonlinear system, when the equilibrium point changes or the operating point changes, you have two different linearized systems actually. Okay. So, this linearized system is valid about this operating point and this linearized system is valid about that operating point. So, the message here is again and again I repeat, as the reference point changes, the linearized approximation also changes actually. Okay. So, you can also visualize this as a problem for let us say inverted pendulum actually, like if you have inverted pendulum, we know there are two equilibrium points, one is vertical equilibrium when the pendulum is in the down, and it's another is vertical equilibrium when the pendulum is up actually. Okay. So, about vertical equilibrium when the pendulum is up, the linear system will be different, when it is down it will be different also. And also you can visualize a problem where the pendulum was inverted from the beginning and then it slowly goes to the vertical down actually. So, that means about the entire trajectory you can also talk about a time varying linear system. Okay, wherever your bob is, that pendulum bob is actually, about that you can find out the corresponding theta, and then about that you can linearize the system actually. Remember that will be a problem in theta dot and all that, where the theta is taken from a reference line actually. Anyway, so that is the message that I wanted to give in this particular example actually. Okay. Now, let us continue with a little further development, okay, where you are interested in a vector problem now, but still it is a homogeneous system, that means there is no control term. Okay. With control term, that will be our ultimate objective actually. Okay. So, what you have here? We have something like x dot equal to f of x, okay, where x is n dimensional, okay, and f is also n dimensional. Remember, x dot is n dimensional also basically by the way. Okay. So, what you are telling here, x 1 dot is something like f 1 of x, okay, right, and x 2 dot is like that actually. So, what you are telling here? We are telling here that x dot x 1 dot is f 1 of x, x 2 dot is f 2 of x, like that actually, up to x n dot, okay, equal to f n of x, where x is nothing but x 1, x 2 up to x n actually. Okay. So, that is the problem that we are talking here. Each of the differential equation, what you see here, okay, each of the differential equation can be like a function of all the state variables actually essentially. Okay. So, let us go back to that. So, that is what you are doing here, x dot equal to f of x, where f is f 1 to f n. In a compact notation I have written like a row vector with a transpose, but essentially it is a column vector. X is also a column vector that way by default. Whenever there is a vector, we interpret that as a column vector actually. Okay. Now, what we are doing here? We also have the very similar analysis basically. What we really want to interpret is again very similar. X is equal to x 0 plus delta x, where this delta x is a deviation about x 0. Okay. Delta x is the deviation of x about x 0. That is the meaning of delta x actually. And again we will end up with this expression f of x 0 plus delta x. Okay. So, what you do here, again we expand that, okay, that is nothing but f of x 0 plus del f by del x evaluated to x 0 like that. And then again we will okay, remember this is now a Jacobian matrix actually. Okay. And then higher order terms will consist of Hessian matrix and things like that. It will consist of, say for example, the first order term in the higher order series, okay, will consist of something like this, okay, del f by del x, okay, f of x 0 plus delta x is equal to, okay, let us say, okay, this is equal to f of x 0 plus del f by del x evaluated at x 0 times delta x, plus the second order term, if you want to write actually, this will become delta x transpose del square f by del x square, this is a Hessian matrix now, evaluated at x 0, okay, times delta x whole divided by 2 factorial, that is the term actually. Okay. Then it will continue with a third order thing, which you have to write it in a series of matrices and things like that. So, these are you can talk about higher order term, but as far as the linearization is concerned, we consider everything as higher order terms actually. Okay. So, what you are left out, I mean that means we have started with x dot is f of x, okay, and we are considering x equal to x 0 plus delta x, and then this one is like that. So, that means if you substitute this term back in here, what you are getting? We are getting x 0 plus delta x dot, x 0 dot plus delta x dot is equal to all these terms what you have here, okay, entire term actually. But these higher order terms are neglected. So, what you are getting here is something like this term will come here actually, okay, because higher order terms you have neglected anyway. So, what are you having then? Now, you are telling that okay, x 0 dot is equal to f of x 0, because that is an operating point that is there. So, if I can probably I mean I can substitute that and cancel out. So, what I have left out is delta x dot is equal to del f by del x evaluated at x 0 times delta x. So, that is the differential equation that I consider as linearized system, with that assumption that this is nothing but my A matrix actually. Okay. So, we are just we will just do that. Okay. So, that is what we are doing here actually. Okay. So, you started with x dot equal to f of x, x is nothing but x 0 plus delta x, okay, and then this f of x 0 plus delta x is that, and we neglect higher order term. So, we are left out with that, okay. And then we are telling that this is the operating point, x 0 is an operating point. So, this fellow is equal to that. So, we will cancel out that one, okay. And again we redefine that actually, right, like what we did before, we redefine delta x equal to x for our convenience, and we are left out with x dot equal to, I mean delta x dot now becomes x dot, and x dot equal to A x, where A is this matrix actually, this is evaluated that way, okay. So, fairly straightforward. What we did for scalar is also valid for vector. Only thing we have to remember is that del f by del x is no more a scalar quantity. It is defined like a Jacobian matrix that way, and that will result in an A matrix actually. Okay. So, let us see an example again. Well, these are this example and the one or two examples that will follow. We have also discussed that in while we are discussing the original state space equation actually. There was one class we have discussed about state space form of system dynamics, and so some of those nonlinear systems I will discuss here actually, and then try to linearize about some operating point for those systems. So, that is one of the examples we discussed there is van der Pol oscillator. Okay, this is a nice problem in the sense, okay, those of you want to know or something, it is like it satisfies something like a what is called a limit cycle behavior, and limit cycle behavior is something like if you take, okay, this is, remember this x 1 is x and x 2 is x dot, that is what we have already defined, right. Suppose x 1 is x and x 2 is x dot, and then with that standard form we can write that x 1 dot is x 2, okay, that first companion form whatever. So, we have defined x 1 is x and x 2 is x dot. So, x 1 dot is x and x 1 dot is x dot and x dot is x 2. So, that is why it is, and x 2 dot is x double dot, and x double dot you can write everything to the right hand side and tell, okay, x 1 is x and x 2 is x dot. So, I can substitute back and I will get something like this. That is what we had done on one of the previous classes actually. So, this is the nonlinear system, okay, and the beauty of this system is if I just plot these variables, this is called phase plan diagram and all that, okay, x 1 of t in one axis, okay, so x 1 of t in one axis and x 2 of t in other axis, then it results in something like a if you can see that it will result in a trajectory actually, in a closed trajectory, and it will also have like 0 0. For example, if you substitute x 1 0 x 2 0, okay, then it will also satisfy this differential equation. Okay, let us x 2 is 0, x 1 dot is 0 0 actually, that is what you are telling. So, this is 0 and this is also 0. So, 0 0 is certainly an equilibrium point. But other than that, if you try to solve this you still put 0 0 here left hand side and try to solve this equation, okay, then it will also result in a closed loop trajectory sort of thing, okay, and this is also like an equilibrium point actually. Any point on that trajectory will also satisfies this this nice behavior actually. That means okay, So, the system trajectory can keep on evolving like that and it will never stop actually. These are some of these departures of nonlinear system over linear systems actually. Okay, linear system we have only, I mean, either two options, either it can, any trajectory that starts with somewhere can either go to origin or it can go to infinity, that is the option actually. But here the trajectory, system trajectory, it may so happen that it can start and still it will go and it will merge there, and once it merges it will just revolve that, and it will start with that and it will merge somewhere, and once it merges it will revolve that actually. That means this step, I mean, there is something called stability of limit cycle behavior as well. So, that means if you start with any initial condition, it need not necessarily go to origin. In fact, the origin turns out to be an unstable equilibrium point here. Okay. So, other than the origin itself, anywhere it starts, it is supposed to converge to the limit cycle only. It will never go to origin actually. So, this is that is why this is also like a benchmark control problem. Here we do not talk about any control here yet. Okay. Okay. We are not talking about any control input, but if you really want to design a control actually for this, unless the control design is good, the system trajectory will never go to origin actually. Okay, that is why one of the benchmark problems is van der Waals oscillator actually. Okay, and there are some practical implications also. Some of the springs and all they behave that way actually probably. Anyway, coming back to this, we want to probably design a linearized control system to make the system trajectory go to the 0, not to the limit cycle. Let us say that is our problem actually. Okay. So, we should know a linearized system first about the origin. Okay. If you really want to design a linear control system, we should know a linear system about the origin, which is happens to be an equilibrium point here actually. Okay. So, that is our problem. About the origin, can we derive a linearized system for this particular system dynamics? That is what we are talking here actually. Okay. So, what you are doing here, x1 0 and x2 0, okay. These are 0 0. Okay. That means, this is the origin that you are talking here. Okay. x1 is 0, x2 is 0 also. Okay. So, we have the I mean this A matrix formula, which is like Jacobian matrix. Remember, this is f1 of x is x2 and f2 of x is whole lot of that. Okay. So, that is the formula that I will use in this actually. So, this will consist of del f1 by del x1 and then del f1 by del x2, the second term. The second 2 by 2 1 element will contain del f2 by del x1 and the 2 by 2 will be del f2 by del x2, that is all we have to do actually. So, this is our f1, this is our f2 here. So, we have to just substitute that actually there. So, if you do that, then obviously del f1 by del x1 is 0, this is x2. Del f1 by del x2 is 1 obviously. So, that is what you get 0 1 here. Now, del f2 by del x2, let us say this, let us say we do the second one, this is easy actually. So, del f2 by del x2, this is only the x2 term here. So, all this will be 0, we are left out with that actually. Okay. So, that is the term what you get here, and then del f2 by del x1, if you see, one term will come from here, okay, another term will come from here, which is nothing but 2c x2 by m, that is the coefficient, into 2x1 actually. Okay. So, that is what you get here, 2c x2 into 2x1 divided by m, okay, and then one more term coming from this one, minus k by m actually. So, that is what we have here. Okay. So, what you are having, interestingly it turns out, okay, that what you are having is the first, if you once you evaluate at 0 0, you have to evaluate, remember that actually. So, this one is all 0, this is also 0, this term happens to be just 0. So, this is left out with 2c actually. So, you are having a matrix, okay, which is in this form. So, the linearized equation talks about x1 dot x2 dot taken together is nothing but that actually. Okay. So, what you see here, so there is a little bit observation also here. Okay. If I just write it in equation form, x1 dot is something like x2, this linear system as well. Okay. And x2 dot for the linear system is nothing but 2c by m into x2 again. Okay. Right, I mean 2c by m x2 basically. So, it essentially what you mean, this entire row becomes kind of 0 0 actually. So, in other words, there are some properties will get suppressed actually by doing this. Okay. Linear systems are nice, but you also suppress various properties by doing this actually. Okay. Suddenly this if you see the nonlinear system, it is tightly coupled with x 1, remember that the x 2 dot, okay, x 2 dot if you see this equation here, okay, it is really tightly coupled with x 1, x 1 appears here, x 1 appears here, all that actually. But the nonlinear system, I mean even though nonlinear system depends on that, x 2 dot depends on x 1 strongly, the linearized system x 2 dot depends only on x 2, which is actually I mean not a good thing to see. Okay. So, linearization is not a very good thing for all practical applications, that is the message actually. In fact, if you carry out further analysis and all, it may also lose controllability, things like that, because the one column is also 0. So, I am not very sure, that depends on the way the control will appear here, we do not know which way it will appear. But if it may so happen that it may lose, the system may not be controllable also using linear system theory, but it is very nicely controllable using nonlinear systems theory, we will see that later. Okay, so, this is all about vector things. Now, we will continue further discussions on how do you do that in general systems. Okay. That is our ultimate objective. Remember, we started with that objective really. So, we have the system dynamics, we have an operating point which is x 0 u 0 combination, not just x 0, x 0 u 0 combination operating point, and then about this operating point can we get that, that is what our aim was actually. So, now we will talk about the real problem, the full problem actually. So, obviously, we are talking about a nonlinear system and an operating point or a reference point is x 0 u 0 combination, x is of n dimension and u is of m dimension, remember that. Okay. So, the analysis is fairly straightforward, again whatever we have done before is also relevant here. So, what is happening here? Okay. This right hand term will again result in this term, okay, with the same assumption that x equal to x 0 plus delta x and u equal to u 0 plus delta u. So, we are interpreting this x as a perturbation about x 0 and u as a perturbation about u 0, right, delta x equal to x 0 plus delta x and u equal to u 0 plus delta u. So, if you substitute this x and u combination here, that is what will result f of x 0 plus delta x comma u 0 plus delta u, and this particular term, okay, I can expand it using Taylor series that way. Okay. So, that means x 0 u 0 is the first combination, okay. Then del f by del x evaluated at x 0 u 0 times delta x, and there will be one more linear term del f by del u evaluated at x 0 u 0 delta u plus higher order terms. Now, how do you all get this? I mean, that is also, I mean, you do not have to keep on doing this, in the sense once you have this, you can also derive that fairly easily actually. Okay, how do you do that? Okay, one way to look at the problem is something like that. I have x, I have u combination. Okay. So, I can also visualize another big vector something which is like I will put them together, x first and u next actually. Okay. Then what I am telling here, f of x u what I have, okay, is nothing but f of this big vector actually, I mean in a way. So, I can evaluate this del f by del x rather, okay, obviously x 0 dot, I mean well, if you want to evaluate expand that, okay, x 0 plus delta x big delta x like that actually. So, this is obviously f of x 0 plus this one evaluated at x 0 times delta x things like that. Okay. And then this term what results in actually is will be a big vector. Okay. Again this will nothing, this is nothing but delta x first and delta u next actually. Okay. Right, and x and u are decoupled terms and all. So, if you see this partition matrix, something is here, nothing will be there actually. Okay. So, this particular term will get coupled with delta x and this second term will get coupled with delta u actually, partition sense. Okay. So, that is how you will get the other one actually. Okay. So, we get some term like this. So, this entire thing f of this x 0 plus delta x comma u 0 plus delta u, we will expand it that way. Again the same trick, we will neglect the higher order terms. Okay. And again remember this pair is an operating point. So, that means this pair will exactly satisfy the differential equation. So, that means x 0 dot is equal to f of x 0 u 0 anyway, that is what we will do here. Okay. So, we will neglect the higher order term and make this equal to as approximately equal to. Okay. And after that this will exactly satisfy that. So, that is there, we will cancel out, and then we will define this as A matrix, and we will define that as B. This is nothing but A matrix, this is nothing but a B matrix. Remember, these are numbers because these are evaluated, some formulas evaluated at operating point x 0 u 0 pair actually. So, these are always numbers actually. They can be time varying numbers or time invariant numbers depending on various conditions, whether you have time varying parameters already or whether you are interpreting this x 0 u 0 as time varying trajectory sort of thing, nominal trajectory sort of thing. Either way it will result in time varying quantities and all that. Anyway, the same thing, I mean, after you neglect this, we redefine this delta x as x and delta u as u. So, this linearized system, okay, we will conveniently write as that x dot equal to x plus v u, with the assumption always that this x is nothing but delta x and this u is nothing but delta u actually. Okay. And A matrix is as evaluated before, but this will also be evaluated at x 0 u 0 pair now. It is no more a function of only x 0, it is x 0 u 0 pair, okay, A matrix. And similarly, B matrix will be x 0 u 0 pair actually. Okay. Now, also remember that A matrix is always a square matrix, whereas B matrix need not be a square matrix. This is the system dynamics will tell. Suppose you see this dynamics, for example, x is an n by 1 vector. So, x is also an n by 1 vector, x dot is also n by 1 vector. So, obviously, the A is n by n actually, whereas u is an m dimensional vector. So, the corresponding B matrix is actually n by m really, and most of the time the B matrix happens to be non square actually. Okay. All right. Now, we will continue with another example. Okay. This happens to be this is again an example we discussed in while you are discussing this state space form of system dynamics actually. So, this happens to be like a rigid body dynamics. Okay, essentially you can visualize this as something like this. You have a box sort of thing, let us say, okay, some satellite is something like that. Okay. Visualize something, or it can be any arbitrary shape thing. So, you have a axis frame, okay, one going towards that, one going towards that, and one coming out towards that. Okay, let us say this is x, this is y, this is z sort of thing, 1, 2, 3 sort of thing. Okay. And if you simply apply this torque tau 1 here, okay, and then let us say tau 2, okay, here, and tau 3 here. Okay. Then you want to see what all system dynamics results. And these are, remember, these are velocity level equations, and if you connect to the flight dynamics what we discussed before, these equations are nothing but like the velocity level components. Essentially in the aircraft dynamics we have interpreted that as p dot, q dot, r dot, that kind of a thing actually. Okay. So, similar thing you can interpret as omega 1 dot, omega 2 dot, omega 3 dot, and this the resulting equation will be like this actually. Okay. And this I1, I2, I3 are nothing but moment of inertia about principal axis, and omega 1, omega 2, omega 3 are nothing but angular velocities about the principal axis. That means, this is torque actually. So, you can also have this velocities, right, that is what the dynamics we are talking about. So, there is a velocity omega 1 here, omega 2 here, and omega 3 here. To control that these quantities omega 1, omega 2, omega 3, we are applying tau 1, tau 2, tau 3, which are nothing but torques actually. Okay. So, the resulting system dynamics happens to be like that. Obviously, this is a nonlinear system. There are there are multiple terms here actually. Okay. That means, omega 1 dot is not a function of omega 1 really, but it is a function of omega 2, omega 3 and things like that actually. Okay. So, we want to linearize this system dynamics. Okay. That let us say one of the objective is for control design is arresting the tumbling actually. That means, this is if it keeps on rotating in a different direction, like one direction it rotates that way, other direction, and then the other direction, it will all get coupled actually. So, it is something called tumbling effect actually. So, if you want to control that tumbling effect using linearized system dynamics, we really need to have a linearized system to begin with actually. Okay. So, let us try to do that, means this arresting this rotation motion actually. So, anything that happens to be, I mean we are not particularly interested in a specific direction or orientation, let us simply arrest the tumbling, that is all. It should stabilize somewhere, the exact orientation where it will stabilize we are not bothered so much about this actually, and that is the problem, let us say. But we are not talking about a control design per se, we are in this particular lecture we are talking about deriving a linearized system, that is all we are doing actually. So, these are the definitions and all. So, we now let us discuss that okay, operating point is nothing but 0 0 0, that is what we want, and the control values around that should also happen to be 0 0 0 obviously. I mean if it is a good control design, then after the tumbling is arrested I still do not need any torque actually. So, it should happen that way. So, that is a good pair to work with actually. So, this is your x 0, this is your u 0. Okay. Now, let us try to apply the formula, okay, whatever formula we have, and that the A matrix is given like something like this way and the B matrix is that way. So, this is del f1 by del x1 like del f1 by del x2 like that, and similarly del f1 by del u1 del f1 by del u2 like that actually. So, if we start applying that, okay, then it all happens like let us say for okay, B matrix first, I will come back to that. B matrix is fairly straightforward because we have only tau 1 here, tau 2 here, tau 2 3. So, if you take f1, okay, del f1 by del u1 it is 1 by I1, but del f1 by del u2 there is no u2 term here. So, that is all 0 basically, and similarly u3 is also 0. So, that is why you get this only one term here, the other terms are 0. Okay, first of all we have 3 states and 3 controls. So, that means B matrix is also a square matrix, remember that in this particular case. Okay. So, similarly if you go back to this second equation, you tell del f2 by del tau 2 is there, but other things are not there. That means my this term is 0, this is the only term what I have here, and the last term is 0 again. Okay. And similarly if I the third row of the B matrix. So, this matrix is fairly straightforward. Now, what happens here? Okay. So, this is like del f1 by del x actually evaluated at omega 1, omega 2, omega 3, 0 0 0. Okay. So, first of all there is no term for omega 1 here. So, that means this term is again 0, okay, and this there is no omega 2 term here, remember that. So, the second 2 by 2 element is also 0, there is no omega 3 term here, okay. So, 3 by 3 is also 0, it need not be evaluated anywhere, the terms are simply missing. So, these diagonal things are all 0 0. Now, what about off diagonal term? Let us consider this one, this is this term partial derivative with respect to omega 2. So, what is left out is omega 3. This coefficient multiplied by omega 3, that is the term which is like partial derivative of this term with respect to omega 2 basically, but that is getting evaluated at omega 3 also 0, omega 3 0 is nothing but 0 here. So, that is also evaluated at 0. So, that term becomes 0. Okay. Similar thing if you just talk about omega 3 term, okay, that means this is the term that is left out after I mean the partial derivative with respect to omega t. So, there is omega 2 term, but omega 2 0 is also 0. That means this term happens to be 0 actually. Okay. So, this diagonal terms are 0, this term all the terms happens to be 0 actually. Okay. So, whatever intercoupling that you had here is all gone actually by linearizing. Okay. So, what are you having now? Otherwise you are just having a B times U matrix, x dot equal to B U simply here, and B matrix happens to be diagonal. That means you have a neat decoupling of the system dynamics actually. Okay. And this is omega by definition, okay, omega 1, okay, by definition is also theta 1 dot actually, you can visualize that way. So, omega 1 dot is nothing but theta 1 double dot. If you have some reference line or something there, you can omega is nothing but theta dot. So, what are you having here? This omega 1 dot is nothing but theta 1 double dot is equal to 1 by I1, okay, times tau 1. Okay. So, this particular thing is called like a double integrator actually, right. Theta 1 double dot is a function of only tau 1. Okay. So, that is a nice, suppose you take a transfer function analysis and all that, this is a nice linear system, you can take a transfer function there, all that it will have a double poles at the origin, and that happens for every channel. it just not happens for one channel. Omega 2 dot is also like that, omega 3 dot is also like that actually. So, this double integrator problem that you might have studied before, or we are going to see the, I mean I do not know whether we are going to see that or not. In standard control literature actually it is very popular because of several reasons. One of the reasons is like that we want to apply linearized control theory for this this satellite control problem, let us say, then this double integrator is relevant to that actually, what I mean. Okay. So, this essentially leads to a double integrator problem. Okay. This is, but remember that this is really not nice, because again you have neglected all the coupling effects for omega 2 omega 3 on omega 1 and omega 3 omega 3 omega 1 on omega 2 like that actually. So, these coupling effects are simply gone actually. So, that is why this linearized control system using double integrator does not work very well for arresting large tumbling actually. There is a small oscillation around which it is okay, but normally remember satellites are in 3D space, any small disturbance can really lead to a large tumbling and things like that, and this is where the linear control theory is typically not sufficient actually. Okay. So, now the last example, we have also discussed this flight dynamics in detail in the previous lectures and all. We all know that these are the things, system dynamics given in 12 intercoupling state variables, and typically it will have 3 or 4 control surface depending on whether you are talking thrust as a control or not actually. If it is thrust is also a control vector, you have 4 controls, otherwise 3 control deflections primarily. So, you have 12 state variables and 3 control variables. We have also discussed before that the first 6 are dynamic level equations, the next 6 are kinematic level equations and things like that. So, it is all getting coupled here and it is too much to deal with. So, we have observed in the flight dynamics lecture as well that the 3 equations are really decoupled from rest of the things, and these are psi, x and y. So, if you take out these 3, then you are left out with 9 equations really. And out of those 9 equations, you can visualize something like a perturbation around let us say straight and level flight. So, height is known to us probably. So, that means height is also gone. Okay. So, you are left out with 8 equations, and out of those 8 equations we can linearize, and probably that linearization also leads to decoupling of the system dynamics into longitudinal lateral. So, let us quickly review that. I mean we have this system states, and what we are doing here is perturbing these variables all over. Okay. Now, these variables with a suffix 0 are nothing but operating variables actually. Okay. That is what we either you have to select or you have to solve for, either way. So, what we discussed before is like, okay, one way to do that is to assume straight and level flight and assume all these conditions are 0. Then we select these variables, okay, and we enforce these equations actually. Okay. Then we will be left out with these variables for to solve for. That means, you are talking about 1, 2, 3, 4, 5, 6, 7, 8, 9 equations, and this is the 9 variable 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 equations there, I mean 9 free variables and 9 equations actually. So, you can solve for which will be valid for this particular thing with under these assumptions, and this will result in this x0 u0 pair combination actually. So, first thing to find out in linearization process is what is my operating point actually. If that is not there, linearized system dynamic does not make any sense actually. So, this process what we call a stream condition and all that is one of the ways to find out this x0 u0 pair combination actually. Okay. And then once you have that, you also have this aerodynamic forces and moments and things like that, whatever this system variable will system dynamics will consist of this x, y, z element. Actually, by the way, there is a small print mistake in this particular slide, probably I can correct that. This f x actually we have talked that as x, okay, and this f t x is something like x t actually, that is what we derived in one of in our flight dynamics lectures. So, this is like y and this is like y t sort of thing. So, like that actually, and then this L A is actually L and this is L T and things like that actually. Okay. So, that is what we are doing here, and this delta x, delta y, delta z further we expand using this component build of ideas and all that. So, this delta x is a function of delta u, delta w, and these are like primary dependence actually. Okay. all right. And then this delta y is there like that, we expand that way, delta z we expand that way, okay, when we keep primary function dependencies and all that actually. So, similarly these moments also these are primarily these aerodynamic forces and moments, and this is how we build up these components actually, okay. And then we write this way, that ultimately if we apply this standard equation, I mean this theory what we just learned, del f by del x is nothing evaluated at x 0 u 0 is A matrix, and del f by del u evaluated at x 0 u 0 is B matrix, okay. And we consider only these 4 variables in one group and the other 4 variables in another group. So, these 4 variables will result in that, the other 4 variables result in other one, and this I mean this also assumes that we have both aerodynamic and thrust control actually, okay, elevator deflection as well as percentage of maximum thrust actually, that is what we put there. So, this will result in that A and B matrix, and further we analyze, okay, when we decouple this 4 into 2, 2 by 2 and things like that, we discuss about phygoid, short period, all sort of things actually, we will not discuss so much into that here. And now with this is something called longitudinal dynamics, because it all happens in pitch plane actually, xz plane. Now, similarly we can also talk about this group of variables along with these two control surfaces, both are aerodynamic control surfaces here, and then we talk about, okay, this is my A matrix and B matrix, okay, and that is my linearized system dynamics, okay. So, but also remember that this x what you see here and this u what you see here, and typically we have we denote that as u c, not u, because u is forward velocity, I mean by flight dynamics notation, we do not want to confuse that actually. U c stands for control. So, this is what you have here, okay. And then this x and u c what you see here are very different from what you see in this system dynamics actually, okay. So, this x means the nonlinear x as it is, whatever it is, and this particular thing, this x means this part of variables actually, okay. And this do not get confused with this x with that x, I mean these are all like bookkeeping sort of thing. This x is the aerodynamic force along the vehicle x axis, but that x means this is like the state variables, part of state variables grouped together basically, okay. I think these are very self explanatory, these are not nothing to get confused with. But if you consider x u, okay, whatever x u you see here, this is del x by del x, this x is aerodynamic force actually, okay. Let me also probably write it here. This x is aerodynamic force along vehicle x direction. This x is a thing, a state vector. Probably we can define a different variable not to get confused with that actually, okay. All right. So, this is how it happens there, and similarly also remember this x when you talk about lateral dynamics, and that x what you talk about longitudinal dynamics are also different. So, these are kind of implicitly we know what we are doing, we don't have to keep on defining new variables actually. If you talk about a longitudinal dynamics, that is the state vector. If you talk about a lateral dynamics, that is the state vector, and similarly the control vectors are also different actually. So, with that we have a linearized longitudinal dynamics and a linearized lateral dynamics. So, we will probably we are ready to apply linear system theory to analyze the system further, as well as to design control systems also actually, okay. So, what are the points to remember here, the entire linearization process. As I have been repeating this, okay, linearized systems are always local approximations about the corresponding operating point, okay. A linearized system is always a local approximation about some operating point. So, without operating point linear systems do not make any sense actually, okay. Now, as the operating point changes, obviously the linearized model also changes, but so that means this linearized model keep on changing for the same nonlinear system. Nonlinear system does not change, but the linearized system can keep on changing actually. So, that is one way of getting the time let us say time varying linear system if you want to do that, and time varying resulting linear systems result from various conditions. One condition is this operating point keep on changing, and the other condition is the system dynamics itself can have time varying parameters. For example, if you talk rocket dynamics or something, as the rocket flies, you have a large amount of mass coming out actually. Okay. So, thrust is also a function of time as well as the mass of the vehicle, and hence the moment of inertia, because the mass is gone. So, Cg is somewhere there, the Cg also keeps on travelling actually, because Cg is a point about which the net moment is 0 actually. So, the Cg variation, mass variation, all these things are embedded into the system dynamics, and that will also be there as part of the A and B matrices actually. So, if you have time varying parameters in the model to begin with, okay, or you have this system operating points keep on changing anyway. So, then you have time varying linear systems actually. Okay. Otherwise, you have time invariant linear systems. Okay. And then the third point is okay, what if you have once you have a linearized system dynamics, obviously the objective in control design using linearized dynamics is 99.99 whatever percent is deviation minimization. That means, you have a deviation dynamics now, and using those deviation dynamics you just have to suppress the deviation actually. So, that is something called a regulation problem, and that is also like a stabilization problem. Any deviation around that, around the operating point, I want to suppress actually. So, that is the usual objective that is put in linear control system design. Okay. Even if nobody tells us explicitly, that is by default actually. Have a linearized system, the objective of the control design is to suppress the deviation, or delta x goes to 0. That is why you see x going to 0, always is there in linear system design kind of assumptions. Linear system control design, the usual objective is to take x to 0. X means delta x anyway, because that is a linear system, x means delta x, and delta x goes to 0. That means, you have a deviation minimization problem, deviation suppression or regulation problem essentially. And the fourth point is because these linear control systems are based on linearized system dynamics which keep on changing with time, anywhere you use a linearized system dynamics to design a control system, you must also follow the philosophy of gain scheduling. Okay. Because the whatever linear system you get for one particular operating point is different from different operating point. So, if you want to have a control system which is valid all over actually, then also you have to bring in the concept of gain interpolation, or what is called as gain scheduling. Okay. And then interpolation variables are a issue themselves, what variable select for interpolation, things like that. In flight control design, typically we follow Mach number and dynamic pressure as the free variables for which we want to interpolate the gain. That means, if different gains what you select are considered as functions of Mach number and dynamic pressure, and then you using these two free variables as as interpolating variables and all, we keep on interpolating the gains at different operating points actually. We will talk more on that as we go to the gain scheduling lecture actually. But that is usually the way to exploit this linear system dynamics actually. That is why we were interested in linearization and things like that to begin with actually. I hope this is clear. We know how to do linearization and what are the implications for linearization, how do we make use of that and things like that. I think I will stop here for this lecture actually. Thank you.